In the past, we had a lesson where we drew free body diagrams under statics. So I'm going to link that video below in the description, and I want you to watch that video first, practice through that before going through this one. Because now we're in dynamics. And in dynamics, we're still going to draw free body diagrams, but also we're going to have the equations of motion. Things are moving now. Here's your challenge. As we go through each loading case, I want you to draw the free body diagram as it asks, and also write all the possible equations of motion. Note, we have rectilinear motion. We're looking at kinetics of particles, not rigid bodies, meaning there's no rotation. Kinetics of particles, the fundamentals that we have to master for the FE exam. This is really fundamental stuff we have to know. Also, there's friction. For all of these, don't neglect friction, and the direction of motion, I'll tell you this, is implied by the force direction. So if the force is acting in a direction, that's going to tell us the direction of motion, which in turn tells us where friction is going to point. So account for friction when doing these free body diagrams. So as we go through each one, pause the video, struggle through it, then check your work with mine to see what you get. Now let's go one by one step at a time. Note rectilinear motion. Let's start with the first one. So looking at this one, we have this case, so it's a very basic case. They might test that, fundamental, where we have the force going to the right. Already I know motion. There's motion, we're in dynamics, so it's going to go to the right. So what we'll do is actually account for that through something we call the kinetic free body diagram. So let's start here with the force free body diagram on top. So I'll label that for us first. Force free body diagram. And below that, we'll draw the kinetic free body diagram. The force free body diagram is actually the same as the static one. Static equilibrium. It's the same, just all the forces acting on the body. So real quick, we should know how to do this. So we just draw the body. So it's going to be a rectangle, free it from its surroundings. We have the force going to the right. So I'll denote that. We have what? The weight of the box, so let's just denote it here, and it acts at the centroid. See, this is the weight of A, box A. We have the normal action down. There's a normal reaction counteracting that weight, and that would be NA. Okay, we have the force going to the right, and that tells me the motion will be to the right. That means the force of friction is going to oppose that direction to the right, so the force of friction goes to the left. So how that would look is going to be like this. The force of friction, and we know the force of friction is always mu kinetic. In this case, mu kinetic. We're looking, things are moving. So we're going to use the kinetic coefficient of friction, and that would be times the normal force at A, this normal force. So that's that. These are all the forces. It looks good. That's the force free body diagram. Now, since things are moving, we're in dynamics, let's draw something called the kinetic free body diagram. And this is mainly there to allow us to see the direction where movement is occurring, because the sign matters. Acceleration is a vector. We have to maintain that sign. If we don't, likely we'll get the wrong answer, especially for complicated problems. So what we'll do is call this the kinetic free body diagram. And I'll denote that like this. And all we do is denote the centroid. FE handbook uses C for centroid, which will stick to. Other books use G. Centroid. And we'll just draw a vector. And I'll denote that in green. Going to the right. And it's going to be mass times acceleration to the right. And more specifically, it's the acceleration in the x direction to the right. That's all we do for the kinetic free body diagram. So I like drawing both. You can just draw that here and say mass times acceleration in x. You're welcome to do that as long as you know that's the kinetic component. That's on the right side of Newton's second law, the equation of motion. I'll draw it separately for these examples. Just note that direction, know the direction. The sign matters. Now let's write the equations of motion. So we have some of the forces in the x must equal to mass times acceleration in x. Some of the forces in the y equals to mass times acceleration in the y. Let's do the sum of the forces in the x direction must equal to the mass times acceleration in the x. Acceleration and forces are vectors. And we're going to say going to the right is positive. So we're going to use the traditional convention that going in the positive x and positive y here are positive. So here, let's denote that the forces in the x, everything in the x, it's going to be this force, so it's going to be going to the right, so it's going to be positive. Then we have the force of friction. Force of friction goes to the left, as we denoted, so that would be like that. And that equals to mass times acceleration in the x. No, we do have some acceleration in the x, so we're going to keep that. That's an unknown. And likely that's the one we need to find. That's usually the one that's unknown. Now we do some of the forces in the y, and we're going to say going up is positive equals to mass times acceleration in the y. Question, what's the acceleration in the y? That would be 0. If this is 0 times the mass, this whole right becomes 0. The right side is 0. Note that because the box is only moving in one direction, the x direction. So what we'll do here is put the forces in the y. So that's going to be negative WA, negative weight of the box, goes down because it's negative. And then we do the positive NA, it goes up, so it's going to be positive. And that equals to 0. There's no movement in the y. Watch out. So here what's good is we can find the normal force. That would equal to the weight of the box. And this force of friction, note, is going to be the mu kinetic times the normal force at A. Normal force at A, as we broke down here. So if I can get that, so we're going to start with this formula. That's typically the case for these. Start with some of the forces in the y. Find the NA, put that in there. The force here is likely going to be given. The force that's pushing to the right with some acceleration, producing the acceleration, then we can find the acceleration. It's a constant acceleration. It's a constant acceleration, does not change with respect to time. Constant acceleration. So we get the acceleration, then we can do, let's say, kinematics, because we know our kinematics equations use constant acceleration. We can find the velocity, final velocity, maybe the starting velocity is 0. We can find the final velocity after some time, or maybe the final displacement, final position with that acceleration. That's the very important constant acceleration. That's that. And then let's go to the next one. So let's keep practicing. Again, I want you to pause the video, attempt this, then you can check your work with mine. So now we have an incline, and it's going to be inclined at 30 degrees. What we'll do is the same process. On top, let's draw the force-free body diagram. On bottom, kinetic. Keep those separate. So the force-free body diagram, we take our block. This is the centroid of it. We have the force acting on this. Let's denote that like that as a force. We have the weight. No, the weight is going to act towards the center of the earth. So it acts strictly in the y direction going down. So this is the weight of A. We have a normal force. No, the normal force is going to be perpendicular to the incline. So that would be looking like this. Normal force at A. And now we have the very important friction. Unless they tell us neglect it, don't neglect it. The force is going to go up. So likely the motion will be up the incline. So the force of friction is going to go oppose that, going down. Force of friction is always mu kinetic. In this case, things are moving, times the normal force, NA. Now that's that. Everything else looks okay. One thing that I did not do. No, we talked about that in statics. Assuming you watched the statics free body diagram video, any inclined plane problem, reorient the axis. We're going to have a new axes that we have. This direction is the x prime, positive x prime direction. This direction is the positive y prime direction. One perpendicular y prime, one parallel to the inclined x prime. These are the axes you should use for all inclined plane problems, always. So what we'll do is actually look at these forces and go one by one. This points in the x prime, so this is good. This points in the y prime, this way, so this is good. This points in the negative x prime, that's okay. It's still in the x prime, that's good. But this one points in the old sign convention, which was this one, right? That's not good for inclined planes. We need to break down this weight into its respective components in the y prime and x prime direction. So what we'll do is say we have a weight here. We'll call that WA. y prime. This is in the y prime direction this way. It's actually negative because it goes down that way. And this will be w a x prime. So that would be negative going that way. Now, with all that said, note this is the angle theta. Where's theta here? Are we going to put it there or there? Where do you put theta? Here or there? Always with the y component. Theta's right there. So that 30 degrees should be there. We talked about that under the statics. I won't go through that. Just know it's always with that y component. So that's that. That's very important as we continue because we're using this sign convention. Now, with that said, this is the force. We can draw the kinetic just to denote that down here and denote the direction of motion. So it's the same block. At the centroid, we have the mass times acceleration. And note that acceleration is going to occur in the x prime direction. So that would be that in the x prime direction. Kinetic free body diagram, force free body diagram. Now, the equations of motion. Equations of motion, we can start with some of the forces in the y. Typically, that's what we do to find the normal force here at A. Just as that comes with practice, you recognize that. But let me do that first. So some of the forces in the y, and we're going to say going this way is positive. Going this way, going up is positive. This way will be negative. And that equals to mass times acceleration in the y prime direction. They're vectors. Now with that, we do the forces. So this is WAY prime. So that would be negative because it goes that way. Negative WAY prime. Then we do the NA. So that's going to be the normal force at A. So that's going to be positive NA. And that equals to mass times acceleration in the Y. But this is 0 because we have no acceleration in the Y. This block is not moving in that direction. So that would be 0. So we're done with that. Now, the thing about this is that WAY prime is a little tricky. We need to break that down in terms of WA. This is going to be WA cosine of theta. We talked about that before. WA is the magnitude, and it's going to be WA cosine of theta, knowing theta is located there. WAX prime is going to be the WA sine of theta, the opposite of cosine of theta. Talked about that also in the statics video. So that's what we put in there. We can find the normal at A, which we'll use in the next equation of motion equation. So that would be some of the forces in the x direction. And we're going to say going this way is positive. Going this way in the x prime direction. Here, these would be prime. Is going to equal to mass times acceleration in the x prime. Now, in the x prime direction, we have the force. This force goes up, so it's going to be positive, the external force. Also, we have the friction force, so that's going to be negative force of friction. And what I'll do for that is denote it as mu k times n, mu k times the normal at A. So note, that's the force of friction. Keep that negative because it goes down this way. Then what else do we have? We have WAX prime. So that's going to be negative as well. WAX prime. Note that's going to be that. It goes down. And then that equals to mass times acceleration in the x prime direction. So with all that, we know we can get the normal at A. The weight of the block is going to be given. So that weight of the box is going to be likely given. We put that in there. We get WAY prime. Then we can find the normal. With the normal, we plug it in there. So then we can actually, the force is going to be likely given. They have to. You can't have an equation with too many unknowns. Put that in there. We know this term. We know this. We can find the acceleration. And with the acceleration, we can use kinematics and so on to find, let's say, the displacement after time, or maybe the final velocity, and so on. So that's how we would do this one. Let's go to this one. So we have now two boxes. And we have a frictionless pulley where we have both of these. So for this one, we have this, and this is actually bigger than that. So box A is bigger than B. So already, just based on logic, where's the motion going to be? How is this going to move? This whole system. It's going to move down. So these are stuck together. So the acceleration is the same. So these, think of these two. This cable cannot really stretch inwards or outwards. So it's fixed together in terms of that cable. So they're going to go down because this is heavier than this. It looks bigger, so I know the motion is going to be this way, the acceleration. So that's one thing we have to recognize. Let's go with the free body diagram of box A. Let's draw that. So we have box A looking like that. I know the centroid is here. It does have a weight, so I'll denote that as the weight of A. Now, it's not touching anything else. It's not touching nothing else, so there's no normal. But I have to be very careful. There is some tension. So what I'll do just to make this look better, I'll denote the weight of A going this way of this box, but I have tension here, and tension is always pointing away. So I'm going to denote that like this as a tension in the cable. So that's going to be the force free body diagram. The kinetic free body diagram looks like this. The centroid is here, and we have the block here with the mass times acceleration in the y. That's going to be for that. Let's do the next one. So it's going to be block B. Block B is going to look something like this. We have block B, it's smaller. The centroid of it is here. We have the tension. Let's denote that. And no, since it's a pulley, this tension is going to be the same through the whole cable. So it's going to be the same tension in red. I'll keep that in red as that tension. For this one, we have the weight. We have the weight of block B. So let's denote that like this. This is the weight of block B. And that goes in the y, strictly in the y. We have the normal force at B, so that's going to go up. Normal at B. And we do have friction. What direction is going to be the friction force? Since this forces these to go down, they're stuck together, it's going to be going to the right. So that's going to be the force of friction here going to the right, which is mu kinetic times the normal at B. Times this normal at B here, this one. So that's that free body diagram, and that would be the force free body diagram. The kinetic free body diagram, just note for this one, I'll draw that on the right here, is going to be the centroid, and all we do is say it goes to the left. The direction matters, so it's mass times acceleration in the x direction going to the left. So based on the sign convention, it would be negative acceleration if we keep that sign convention that we're used to. So force free body diagram, kinetic free body diagram. Now the equations of motion. This is a little complicated, and you have to be given some numbers really to solve this. We know that one thing about this is this block and this block are stuck together. This cable, it cannot flex. It's inflexible. It's going to be stuck together. So if this moves at some acceleration, we know this is acceleration in the y for block A. This is the acceleration in the x for block B. It's the same acceleration. Note that for this. Like for the FE exam, that's going to be the case. So the acceleration of A here is going to equal to acceleration of block B, and that equals to the total acceleration. They're the same acceleration. That's one thing. And we also said the tension is the same in the cables. Very important. So if we draw the equations of motion, we can start with block A here as shown. So for that, we can do only in the y direction because there's nothing happening in the x. The x is irrelevant for block A. So what we would do is sum of the forces in the y, and that would be going up is positive, equals to mass times acceleration in the y. So we know some of the forces in the y, we have the negative WA, the negative weight, and we have the plus T plus the tension, and that equals to the mass times acceleration in the y. So that's going to be one equation that we have. Now let's go to this free body diagram, and that free body diagram depends on both what's happening in the x and in the y. Unfortunately, we have friction, so we need to do the y to get the force of friction because it depends on the normal force at B. So what I'll do is start with some of the forces in the y first. Just to do that first, going up is positive, equals to mass times acceleration in the y of this block. No, this is block A here. This is block B. Acceleration in the y of B is 0, so the whole right side becomes 0. This block B is only going to the left in the x direction, so that's 0. So we do some of the forces in the y. That would be the negative T, negative tension because the tension goes to the left. We have the force of friction going to the right, so it's going to be positive force of friction, and then that's all. So that would equal Sorry. So that's going to be in the y. So in the y, we have negative WB. So that would be in the x, negative WB. We have plus NB, and then that equals to 0. So we have that. We can find the normal force at B if we're given the mass of block B. Likely that will be given. So that would be that one equation. It allows us to find the normal at B. Then we do sum of the forces in the x must equal to mass times acceleration in x of block B going to the right is positive. Let's denote those. So in the x, it would be negative t. So we put that as negative t. And we have the force of friction going to the right. So positive force of friction there, this one. And that is all. So that equals to mass times acceleration in the x of block B. Now, with all of that, the force of friction we can get because we have the normal force, put the normal force times the coefficient, get that. The tension is unknown. Let's say the tension we do not know. That we do not know. And also the acceleration, we don't know. But we're able to actually solve this because we have two equations and two unknowns. The first equation is going to be this top equation when we drew the free body diagram, and also the equation of motion in the y for block A, box A. Then the second equation is going to be this equation when we analyzed block B. Note, the acceleration is the same for both of these. That's the crucial part. That this acceleration is just A. This acceleration is just A. This acceleration here is A. This acceleration is A. So we have two equations and two unknowns. It's going to be the acceleration and the tension, the unknowns. Tension, acceleration, two equations, two unknowns. We can solve this using substitution, elimination, or the calculator. The calculator, fastest method for the FE exam. So we can do that. In fact, I want to challenge you to do that. Let's say find the tension and acceleration, assuming this is 10 kilograms for A. B, let's say, is 5 kilograms, assuming that. And also, basically, that coefficient of kinetic is 0.2. We need that as well. That's 0.2 for the coefficient. If you have all of that, you can solve this. Give that a shot and let me know what you get. Let's do this next one. So rectilinear motion still. So we have this case now. So we want to draw the free body diagram of box A and box B. Now, for these, start with the free body diagram that you know something about. Since the force is acting to the left, I know this block is going to move to the left. Start with that free body diagram. Very important. It goes to the left. It tells me it's going to move to the left, accelerate to the left. So let's draw that first. So let's denote that here, the force free body diagram. Something like that. This is going to be the center of the box. I know the force is going to go to the left. Now, I know I have a weight of the block. So that's going to be the weight of B. Weight of B. I also have the force of friction. Let me just denote that. It's going to go to the right because the motion is to the left. So the force of friction between the ground here and block B is to the right. Force of friction, I'm going to denote that specifically between B and the ground. Between the ground and block B. Also, I have a normal force. I have a normal force between block B and the ground. G stands for ground here. What else do I have? I have something important, which is the force of friction here. Note, the force of friction between A and B will go to the right as well. So the motion's to the left, the force of friction will go to the right. Just like this one, just like this direction, it's going to go to the right. So I can denote that in the new color. It's not the same force of friction. So this is the force of friction, and that would be between A and B, between block A and block B. That is still important on the free body diagram of box B. I forgot to consider one very important force. It's going to be the normal force between A and B. B is hitting A and A is hitting B. There's going to be a normal force of contact between those two. So we know here, I can denote that just on the side a little bit here like that. And this is the normal force between A and B. No, that's there. That's the full force free body diagram for block B. Now I can draw the kinetic real quick. So that's going to be very simple. It's just going to go to the left. We put mass times acceleration to the left. That acceleration will be negative because it goes to the left. Now that's that. Let's go to box A. So box A is going to be the top one, and that we draw, let's do the force free body diagram, centroid. So it does have a weight. We do the weight of box A, weight of A. We do have the normal force between A and B. It's the same normal force. Remember that when you have things stacked up, it's the same normal force. It's going to be the normal force between A and B. So it's the same one. We put that like that, the normal force between A and B. Same one here as the normal force for the free body diagram box A, and we have the tension going to the left in this cable. That's that free body diagram. The direction of motion for that doesn't occur because this is going to be static. It's not going to move. The only thing that moves is block B to the left. With that said, we're going to have equations of motion. Let's start with this one real quick. This one's easy because in this one, it's only in the y. So what we would do is sum of the forces in the y equals to mass times acceleration in the y. Going up is positive. And we have negative W, A. And we do have plus the normal force between A and B. And that equals to 0. It's not moving in the y. It's just going to stay static. So that doesn't move in the y, so that would be that. What we can do for this is actually find the normal between A and B is going to equal to the weight of A, the weight of box A there, which is good to know because that normal is going to get carried into this free body diagram and in those equations of motion. Very important. So what we'll do for the next one is start with, let's do some of the forces in the x. Must equal to mass times acceleration in the x. Going to the right is positive. Going to the right is positive. Let's do all the forces. So this is the force of friction. So I'll denote that here. Force of friction AB is going to be the mu kinetic between surface A and B. Very important. Likely that's going to be different. So it's going to be between A and B. And that's going to be times the normal force at that location. So it's going to be normal AB. That's that one. Now the force of friction here, let me just put that on the right. Between the ground B, between block B and the ground is going to be the coefficient of kinetic between the block B and the ground times the normal force BG, the one in red. Very important there to keep that consistent. So what we'll do is just put those in there. So force of friction, so that would be positive. Force of friction AB. Then we do the positive force of friction between BG. That one goes to the right. Now this force, the pushing or pulling force is going to go to the left. So that would be negative F here for this one. And that would be everything in the x equals to mass times acceleration in the x. And we do have some acceleration in the x. The direction matters. So what we'll do is just keep that as is. We're going to get a negative for the sign if we assume everything that goes to the right is going to be the case for that. So that would be that one. Then we do the sum of the forces in the y must equal to mass times acceleration in the y. Going up is going to be positive. In that case, we have the negative here and negative. So let's go one by one. Negative NAB. That's this one. Then we have the negative weight of the block B. That's going to be this one. Then we have the normal plus the normal between B and G. And then all of this is going to equal to 0 because we have no movement in the y direction. Now with this, what's good is this. This NAB is going to equal to the weight. And that weight of the block is going to be given to you, likely. So we take that and put it in there because we know that. So if we know this now, we know the weight of block B. That would be given. Let's say the mass is 20 kilograms. This is, let's say, 5 kilograms. These will be given. The weight equals mass times acceleration. We know that. We know this. We can find the normal between B and G. B and the ground. Now with that, we can go back in this because the force of friction is going to be this. This coefficient will be given and this coefficient will be given. We know NAB and NBG we just found. So we can find both of these. The force here is going to be, let's say, 20 newtons. That would be given too in the problem statement. Then with all of this, we can find the acceleration. That's the key thing. These are tough, but they're definitely doable with practice. Now let's look at a basic curvilinear motion problem. We're still looking at the kinetics of particles, but now it's not rectilinear. It's going to be curvilinear, meaning the particle is going to move in a circle, in a curve. So in that case, it's a little different. It's not as bad. We'll look at a very basic problem fundamental to the FE exam, draw the free body diagram and the equation of motion. So looking at this, we have a pendulum, the classic case, where we have this bob. So the pendulum bob A. And notice the direction is going to be given with this arrow. On the exam, likely they'll denote it with a velocity vector. They'll show you the direction. That's going to be important. So it's going to be moving this way, and that would be clockwise. We have this angle as well. It's a pendulum system. Now look at the particle. It's moving in a curve. Anytime things move in a curve in a circular manner, we have to use different equations there. And we draw different free body diagrams. So let's draw the free body diagram, force free body diagram of the bob. So I'll denote that as a circle. And this is A of this. Here's what's important. We have new axes. We do not use this X and Y. That's rectilinear. We do not use this X prime, Y prime. That's still rectilinear for inclined planes. Now we have the tangential and normal directions. So note that since this is moving this way, we're going to say this is the positive tangential direction. T stands for tangential. And also now we have a normal direction. This is a positive normal direction. So in the direction of motion, the assumption is it's going to be positive tangential, and the normal is always going to be positive towards the center of the point of rotation. So imagine like a circle here. It has a center, so that would be the normal direction, goes inwards. So what we do for this, let's denote the tangential direction, tangent, is going to be this, positive tangential. And we also have the normal. So this would be positive normal. Let's denote the forces. Now, what do you notice here? We have a cable. Cables always have tension. So the tension in this cable is going to be one tension. 1 times T is T, just one cable. So that would be the tension, and that would be a force. What else do we have? This bob will have a mass. Mass relates to weight. Weight equals to mass times gravity. So I'm going to denote the weight at the center going down. This is the weight of A. Now notice, as we talked about in inclined planes, since that weight is not acting in the normal and tangential axes, we have to get its component in the right directions that are normal and tangential. So what we have to do is draw the weight vector this way, and we'll call this the weight of A in the tangential direction, and we have a force vector also for the weight. This is the weight of A in the normal direction. So we need to do that. And actually we can break this down. Likely we're going to give it the mass of the bob. Let's say they give us the mass, 1 kilogram, whatever it may be. We can get the total weight. That's no problem. But now we have to get the components, and it depends on the angle. This angle is 30 here. Where would we put that? If this is 30, is the angle 30 going to be here, or would we put it here? So imagine this. If that's 30, you can extend this line like this on this diagram, and we can also draw another vertical. Let's say the north-south line has to be this. That's 30 here. No, what's happening is something like this. We draw this. This is 30. This has to be 30. They're the same. So the 30 would be here. The angle of 30 is going to be there, 30 degrees. So WA in the normal is going to be what? If the 30 is there, it's going to be WA cosine of 30 degrees. And WA in the tangential, that component in the tangential is going to be WA, and that would be sine of 30 degrees for that one. So that's going to be the two components. We need to do that. WA we have. And then what we do is the equations of motion. But before we do all of that, just know we still have a kinetic free body diagram. It's not bad. We just have to show the direction. We're going to say it's going this way. So the acceleration tangential will be this. So this is the acceleration in the tangential. And we do have acceleration in the normal. So it's going to be the acceleration in the normal. So both of these. Then we do the equations of motion. We do the tangential and normal. So what we would do is some of the forces in the tangential direction. This is all in the handbook. is going to equal to what we have under curvilinear motion in the handbook. So that would be the mass times the acceleration in the tangential direction. So we do that as the mass times acceleration in the tangential direction. And the forces in the tangential would be the positive here, positive WAT. And then that would equal, that's it. So that equals to mass times the acceleration in the tangential direction, which is defined under curvilinear motion, particle curvilinear motion, as the change in velocity with respect to the change in time. So that's defined here. A tangential is the change in velocity with respect to change in time, or in derivative form, it's going to be dv dt, the first derivative of the velocity function. So that's going to be what we put in there, the dv dt. So that's the tangential. Note going this way is positive in the tangential. Now we do the sum of the forces in the normal equals to mass times acceleration in the normal. So we're going to say in the normal going this way is positive. In the normal, what's the forces? It's going to be the t here. So it's going to be positive t. We have the WA in the normal, and it goes this way. So it's going to be negative. So that would be negative WA in the normal right there. And that equals to mass times acceleration in the normal. Note the acceleration in the normal is also in the handbook. It's defined with respect to the radius of curvature. That acceleration in the normal is going to equal to the velocity squared divided by the radius of curvature. And this right there is going to be likely given. If we have the velocity, we can put that and we can solve these forces. So that's going to be how we do curvilinear motion. What if now we have a spring? So we have a spring, we have a box A. It says neglect friction and the spring is compressed from equilibrium by 1 foot. Compress, we push it, compressed. So the K value of the spring constant is also given. Draw the free body diagram box A and the equations of equilibrium. Note, if you attempt this, go with the classic way. But I'm going to tell you, this is going to be incorrect. We have to use the principle of work of energy. Let's go through the traditional way. What we would do is going to be draw the free body diagram. So what I'm going to do is denote the box here of the box. So the centroid is there. So it does have the weight. So this is the weight of A. And it does have a normal force going up here at A. We have the spring. So no, since it's compressed from equilibrium, let's say the equilibrium position is here. Let's label that as EQ for equilibrium. We compress it by certain distance. That's what this is telling us from equilibrium, which is not drawn in the diagram. So we compress it by 1 foot. And sticking with the handbook, this would be our S value, or the change in S, delta S. That compression amount is going to be that distance S from equilibrium. So that's going to be the case. That tells me I'm going to develop a spring force. Since we have compression to the left, the spring force goes to the right. Compression to the left, spring force goes to the right. So the spring force is going to go to the right, force in the spring, and I'll denote that like that as the force in the spring. And is that all? Neglect friction, so that helps, so that saves us time. And that's what we do for this. That's the free body diagram. So we know this is the free body diagram, and what we would do is do the equations of motion. So sum of the forces in the x equals to mass times acceleration in the x. Going to the right is positive. So the force in the x is going to be the spring force. So it's going to be positive force in the spring equals to mass times acceleration in the x. Note we do have acceleration in the x. We're looking at dynamics, so it does move. So simply here, the mass or the acceleration in the x is going to be the force in the spring divided by the mass. Anything in the y does not matter for this one because we neglect friction. They say that it saves us a lot of time, but in the other ones, we did not neglect friction. In the y doesn't matter really in this one because we don't need the normal force for friction, normal force at A. So with that said, we can find acceleration in the x, but note the spring force is what formula? It's in dynamics, that section is messy, but spring force is defined as K times S. So it's going to be the constant coefficient times the distance or that change in compression, which is in this case that 1 foot. So I'll denote that in blue for us. It's the compression amount of 1 foot. That produces the force in the spring. So I'll write that here in this formula. It's going to be K times S equals to mass times acceleration and in X. So let's make up some numbers. Let's say the mass is 10 kilograms, like that number, 10. And we do have the K is going to be 100 pounds per foot. And S we said is 1 foot. You can find the acceleration. You're going to get some value. This value is wrong. It's incorrect. The assumption here for all these problems that we're doing is the forces. What are the forces? Let's say the external force applied is constant. It does not change with respect to that distance. This is the same force. Let's say we pull it with 20 pounds. That 20 pounds does not change with respect to time, with respect to distance. It's going to stay constant. The normal force stays constant. The friction force will stay constant. The weight here, it does stay constant because we're not really changing elevations. That weight stays constant. The weight we're going to say is constant. Think of all of these forces. When we do the equations of motion, they're constant. Constant. All of these. The problem arises is when we have a spring. That spring force, the force in the spring, is going to depend on K times delta X, or the change in X from Hooke's law, or we can call it delta S. So we know the force in the spring changes with respect to the compression amount or the amount we stretch. It's going to be variable. This is variable, and anytime we have the variable force, don't use the equations of motion. Do not use Newton's second law for basically all the spring problems. We're going to use the principle of work and energy, and we do more of that in the course, in the direct hub course, as we do a variety of practice problems. Just note the new equation we use is going to be the energy, the inelastic or the elastic potential energy in the spring, which is 1/2 Ks squared as provided in the handbook. This is the crucial formula that we will apply in the course using the principle of work of energy when we analyze springs. Anything with springs, we're going to use the principle of work of energy. This is incorrect. It's not going to give us the same answer. In fact, assuming these numbers, let's say use 10 kilograms, use the K is 100, the compression is 1 foot, you're going to get an acceleration here. And when you compare that to the acceleration you get using the principle of work and energy, it's going to be different. So that would be different in that case. The acceleration will not be the same when you compare the two values. You can try that. Just know for spring problems, always use the principle of work and energy.